Hello, thank you for the opportunity to speak at this conference. I'm going to be talking to you about some of the results from my thesis. So our setting is S3 with the standard contact structure. On the right, we have R3, and we're going to be seeing S3 as R3 with a point at infinity. And we have the contact structure, which is given as a kernel of the one form dz minus y dx, and which will associate to every point on R3 a plane, and these planes will tilt as shown in this figure. Our protagonists are Legendrian links, and these are links, so embeddings of S1 into S3 with the standard contact structure, so that their tangent vectors are always contained in the contact planes. So we want something that is going around and the tangent vector is contained in the plane. There's a really useful projection of these Legendrians, and that's the one where you forget the y coordinate. And you're going to see projections with cusps and with crossings that are always over and under as so you don't have to indicate it. And what's really nice is that the slope of the tangent vector recovers the y coordinate. Here we have a Legendrian unknot, and here we have a Legendrian trefoil. Now, when you're studying Legendrians, you want to classify them up to Legendrian isotopy. So this is a smooth isotopy, so at every step you have a Legendrian. And you're going to find that for every smooth knot type or link type, there are infinitely many distinct Legendrians. Here on the right, we have 3 different Legendrian unknots, which are all smoothly isotopic, but not Legendrian isotopic. You can also classify certain surfaces in the 4-ball whose boundary is your link or knot in the 3-sphere, which is the boundary of the 4-ball. And here you can see a cartoon of this for the trefoil with a genus 1 surface that bounds it, and we call these surfaces fillings of the knots or links. When I say certain, I mean orientable, exact, and Lagrangian, where I'm working with a standard symplectic structure on the 4-ball. And we want to study these fillings because they're topologically rigid. They always realize the smooth 4-ball genus of the knot. So for example, a trefoil will only have genus 1 exact orientable Lagrangian fillings. And we want to classify these up to Hamiltonian isotopy, which is a smooth isotopy of surfaces that only passes through exact orientable Lagrangian fillings. And although we have this topological obstruction, this is still really difficult. We have only one complete classification for when these fillings do exist, and that's for the following unknot drawn here, and it has a unique exact Lagrangian disk filling. Even for the trefoil, we don't have a complete classification. We suspect there are only 5 distinct fillings of genus 1, but we don't know if that's it. In the last year, there's been a lot of progress made in showing that there are Legendrian links that admit infinitely many distinct exact Lagrangian fillings. And here's an example of one found by Casals and Ing. My contribution is to find another family of Legendrian links that have infinitely many distinct Lagrangian fillings. Here's their projection. I call them lambda n for n, the number of crossings here. And something to note is that both lambda 1 and lambda 2 in this family only have genus 0 fillings. And they're some of the first examples of Legendrian links with infinitely many planar fillings. There are also some, currently, to my knowledge, the smallest known Legendrian links with infinitely many fillings. Now, you can apply the study of fillings to build closed exact Lagrangian surfaces in the case when you're studying certain symplectic 4 manifolds. You really want to consider Weinstein 4-dimensional manifolds, and these are manifolds with handle bodies that play nicely with the symplectic topology. And so their symplectic topology can actually be encoded as with a Kirby diagram given by Legendrian links in one of these 2 contact 3 manifolds. And we're going to concentrate on S3 with the standard contact structure. Now, we also find Weinstein handle bodies of this complex affine variety, which is also a Milnor fiber of a TPQR singularity, so that you can build infinitely many distinct exact Lagrangian closed tori from fillings, where you're taking a filling and attaching to it the core disk of the 2 handle. And we can also find infinitely many spheres, and these are built from fillings of the lambda 2 example that we saw above. Thank you.